Thanks everybody for coming. My name is Sandy. I work as a data scientist at Cloudera. I've been at Cloudera for about 3 years now. Originally I was working on Yarn and Hadoop itself. I'm on the Hadoop PMC. I switched over to Spark once we started to incorporate Spark on our platform. So I was the original lead for Cloudera's Spark team. And after that I transitioned to a data science role. So for my job, I spend a lot of my time with different companies, different Cloudera customers, helping them figure out how to solve particular problems and answer particular questions using Hadoop and the related ecosystem. Before I begin, a couple things. First of all, I'm really into interruptions in my talks. So if anybody has a question, please just raise your hand or shout it out aggressively if I can't see your hand. We can talk about it. Second of all, so who here works at a bank, first of all? Raise your hand if you work at a bank. Cool. Or other financial service. I see some Bloomberg people over there. Okay, a decent number of you. Who here has written a Spark job? All right, pretty good. Let's go going. So Coming from a data scientist perspective at a platform company, finance is a fairly interesting vertical. If you go to, let's say, a large retailer, wow, this is really eager, and explain to them that they can use math and data to improve their processes, you'll often get this look from them, which is like, what is math? What is data? If you go to a large financial institution and tell them the same thing, you'll get pretty much, the same look. But from them, it's like, yeah, we've been doing this for like 30, 70, 2,000 years. Tell me something new. So for that reason, we're not going to talk about, Hadoop and Spark in financial services. We're going to talk about a specific use case, a specific question that has come up a lot in our engagements, and the ways that we think are nice to solve it. This particular question, the question that we'd ultimately like to answer is, under reasonable circumstances, what is the most that you can expect to lose? When we say most, we're talking about money. So we're talking about what is the most money we can expect to lose under reasonable circumstances. This is a really important question to large financial institutions for a couple different reasons. The first one is that it's directly tied to the question of all the money you have, how much of that money needs to be held as cash, and how much money can you put into investments to make more money. So, it's pretty directly tied to your profits. It's also important because it is something that regulators ask you all the time. The regulators don't ask you just that, but it's maybe the central component of a lot of risk regulations for banks. So it's important to be able to answer it in a bunch of different nuanced ways and come up with nice models for doing so. So we typically formalize an answer to this question through a statistic that we call through a statistic that we call value at risk. We often abbreviate it as VAR. The statistic has 3 parameters. When you report it with 3 things. First of those things is a portfolio. So this is, what are the financial instruments that we're looking at? And for those who are not familiar with some basic finance jargon, when we say an instrument, we're talking about anything that can be owned and has value. So a stock is an instrument, a bond is an instrument, advanced derivative, maybe a swap or an option is an instrument. You have some sort of portfolio of instruments, and you want to understand its behavior. In addition, you have a time period. So we have this big portfolio of instruments, and at this point in time, it has some amount of value. What we're interested in is, let's say in the next 2 weeks, how is the value going to change? What's the lowest that our returns, that our change in value can go? And last of all is the p-value, which basically measures how extreme a situation do we want to plan for. A p-value, if it's 5%, says in the worst 5% of situations, what's the amount of money that we could expect to lose? So to be a little bit more concrete about this, if we say our var for some given portfolio of instruments over 2 weeks with a p-value of 0.05 is $1 million, what we're saying is that at the end of 2 weeks, we think there's a 95% chance that we'll have lost less than $1 million and a 5% chance that we'll have lost $1 million or more. Any questions on that before we keep going? Sort of a nice thing to understand. Cool. One of the commonly criticized things about the statistic, it doesn't really tell you about what happens in the lower 5% of situations. So it doesn't tell you if when things go really bad, you only lose $1 million or you lose several bajillions of dollars. So there are other statistics like expected shortfall that try to capture that information a little better. This is a graphical representation of what it looks like. This is a probability distribution over the returns of our portfolio over the particular time period. And to get a 5% var, we basically chop off this little area, this tail, where the combined probability mass amounts to 5% of the total probability mass in that distribution, and that little cutoff is our value at risk. So to come up with one of these, to come up with a value at risk statistic, we basically need to hypothesize a probability distribution over the returns in the given time period. What are some techniques for doing that? Calculating var generally falls into three main classes of approaches. The first one is this approach called the variance-covariance method. And this approach is really nice because it allows you to derive a solution analytically. You calculate some basic summary statistics about your data. You look at all the instruments, say like what's the average return over this particular time period, what are the variances and covariances. You plug them into this formula and it gets out, it spits out a number. The big disadvantage of this is it makes some very restrictive assumptions about the probability distribution of your data. So it's going to assume basically that all your instruments are normally distributed, which is often highly inaccurate in real-world situations. An approach that is kind of the opposite of the variance-covariance method is an approach called historical var, historical simulation. With a historical approach, you basically say, let's look at the last 100 days of what happened. Let's sort them by their returns over those days. We'll look at if we're looking for a 5% var, we'll look at the days with the 5 worst returns and say that's likely what's going to happen in the future. We basically do basic extrapolation. This is really nice because it fits the data really well, but the problems with it usually involve overfitting, where we come to expect that our performance in the future will be very much like our performance in the past, whereas we might want to try to account for the possibilities of black swan events, incorporate shocks into our model, understand the possibility that things could be way worse or maybe better than what happened in the immediate past. The last of all these approaches is called Monte Carlo simulation, and that's the one we're going to focus on today. The idea behind Monte Carlo simulation, and stop me here, this is a sort of useful thing to understand as we go on, is that we come up with some sort of model that allows us to randomly generate, I'm just going to put this thing down, that allows us to randomly generate states of the world. Basically, we want to have a way of turning a bunch of random numbers into some set of plausible scenarios about what happened. And we want to be able to repeatedly do this, repeatedly generate random numbers and then run them through a process and generate some state of the world and some ultimate outcome for how our portfolio performed. In this case, we're going to call a scenario a trial going forward. We run our simulation millions or billions of times, and then using the results from all of these trials, we can build up some sort of empirical probability distribution that allows us to understand what's likely to happen. So in this situation, we lost $100. In this situation, we lost $2 million. We built up a curve with all those values. The nice thing about Monte Carlo over the other approaches is that it allows us to come up with a fairly complex process for generating plausible trials. So if we think of the world functions in a pretty complex way, which often it does, we can model it through some sort of complex process, and we don't need to do all the math to turn that complex model into an analytical solution where we can just plug in some numbers and find out a result. Often it's impossible to drive an analytical solution in that way. So Monte Carlo simulation is a way of still getting results when we can't directly do math on what we're trying to understand. Any questions about that before we keep going? Great. This is an example of what Monte Carlo might look like. On the bottom, we have returns, and then we have these little bars showing how many of our simulations got that many returns, which forms this empirical probability distribution. So the question then is, once we've decided, oh man. Forward, yeah, no. Any idea what's going on here? Am I doing something wrong? Okay. The question then is, how do we build up a process for turning numbers into plausible financial scenarios? The most common models tend to evolve around what we call market risk factors. And the idea behind market risk factors is that things that happen around the world or within the markets are likely to affect or have enormous impact on the returns of our finer grained investments, like any particular stock or particular option. So normally when you build the Monte Carlo simulation, we like to come up with a set of market risk factors that basically express the state of the world at large as opposed to the state of our particular financial instruments. We can put a variety of things into these market risk factors. We might use the indexes like NASDAQ or S&P. You might use prices of commodities or currency exchange rates. We might use GDPs of certain countries or treasury bonds, things like that. It's typical to have anywhere between 5 and 500 market risk factors. So not big data by any measure, but still a decent amount of things. Pardon me. Given a selection of these market risk factors, we basically need two things. We need a way of simulating the behavior of these market factors. So we want to be able to randomly generate situations involving our treasury bonds and the US GDP and these indices. And we need a way to, given these market risk factors, given the values that we've simulated, to predict the performances of individual instruments in our portfolio. So let's talk about first the second one of those, which is once we have values for our market risk factors, how do we get to values for particular instruments? In this talk, we're going to use a very basic, simple linear model. What this basically means is that we have a coefficient, some number for each instrument for each market risk factor, and then given the values of our market risk factors, we compute this weighted sum plus possibly some sort of constant to determine the value of, or the return of that particular instrument in that particular simulation. In practice, we would probably do something much more sophisticated. For example, we might use a bunch of features that are nonlinear transformations of our market risk factors. For example, if we think that a particular instrument happens to be a quadratic function of one of the market risk factors, we could perform that transformation before and then use a linear model on that quadratic transformation. We could use more advanced supervised learning techniques like random forests, or we can certainly use more finance-specific techniques, like we could use the Black-Scholes equation if we want to understand the returns of options. We're still, yeah. Generally speaking, we don't have that many market risk factors, hundreds at most, but our portfolio can contain a huge number of instruments, thousands or millions. So it would be really nice if we could train the models for each instrument in parallel, if only we had some open source distributed computing engine that made it easy to do such a thing. Spark comes to the rescue. Has anyone here not heard of Spark? I guess that's kind of embarrassing. Or if you've heard of Spark, raise your hand. Yeah, cool. Thanks. So this is some Spark code that basically is in charge of training the models that we use to take market risk factors and turn those into returns for individual instruments. We have some process not shown that's in charge of loading up all the market risk factors into local memory, so that's just a basic array. Then we have some process that's not shown that's responsible for loading up all the returns for the instruments as an RDD. So this is a distributed collection. Both of these are actually fairly interesting, and it'd be nice if we had time to talk about them. There's some important transformations that's important to do on the data when you're during that loading process, but for the sake of time, we're going to elide those details. So we're going to take all these guys, and we're going to basically run this, this map computation, this embarrassingly parallel computation over the instruments. For each of the instruments, we take all of the market risk factors, and we plug them into a simple regression and fit a linear model, figure out the best coefficients. Once we're done with doing this in parallel, we collect all this data, and we bring it to the driver so that we can use these models later in our computation. So at the end of this process, we have a model for every instrument in our portfolio. If we have 1 million instruments, it's 1 million models, and each model has a coefficient for every market risk factor. So if you have 100 market risk factors, we have 100 million numbers that we care about. Now we have our process that allows us to turn factor returns into instrument returns. How do we sample these factor returns? So ultimately, the question here is we want to be able to generate sample vectors where each vector has a component for each market risk factor. And one of the central challenges of generating these random vectors is that factor returns are often correlated. So if the whole market is doing bad, it's likely that the US GDP is suffering, it's likely that bonds are performing more poorly, and so it would be an inaccurate model if we were to simulate all of these separately. Always good practice when trying to come up with a way to simulate these things is to look at the actual data. This is a plot that I generated using Scala's Breeze plot that shows the distribution of US Treasury bond two-week returns. We're using kernel density estimation, which is basically a technique that allows us to take a bunch of points, a bunch of measurements, and extrapolate a smooth probability density function from it. So we can see at the bottom, we have values for our two-week returns, and we can see the probability density on the side. It would be nice to say this is normal, it has a single peak, but that's not really something that we can say without a lot more statistical testing. We can do the same thing for the price of crude oil. Again, it's got this sort of single peak, but it seems to be leaning in a slightly different way, and the tails have a slightly different structure. So with this real-world data in mind, we're going to oversimplify quite a bit and decide that these returns are drawn from a multivariate normal distribution. For those who aren't familiar, a multivariate normal distribution is a probability distribution over vectors of length n. So every multivariate normal distribution is parameterized with some size of the vectors that it's generating, as well as a mean and some sort of covariance structure. A couple facts about it. Given all of the variables except for one, so if you know about all the values, but you're except for one of the variables, that last variable is distributed according to the typical univariate normal distribution. And it's able to model correlations between variables that we were worried about. The fact that if one variable is doing poorly, likely another variable is going to do poorly as well. It's able to model these correlations by taking in an explicit covariance matrix, that's a sigma, that basically models its covariance structure. Any questions about that before I keep going? Not a super question-y crowd. Yeah. Yeah, so the question was, is the framework more flexible on using multivariate Gaussians? Can you use other things? And yeah, certainly. So this is just, we're doing it for the sake of simplicity, but you could easily plug in the multivariate T distribution or some more empirical distribution. In the library that I've built to do this, I've tried to make that pluggable, and I have a few other options there. This is the PDF, the probability density function of a multivariate normal distribution. Just for two variables, we can see x and y on the bottom, and these on the up-axis we have the probability density. So around any particular horizontal cross-section, it has this elliptical structure. Fitting a multivariate normal distribution to our data is very straightforward. Basically, we calculate the empirical means, and then we calculate the empirical covariances between our different market risk factors. We're able to do this through the commons math covariance function, and then this is not shown here for no good reason. We're able to take these means and these covariances and plug them into the commons math multivariate normal distribution class, which has a method for generating random samples, and we'll use that later. I'll show you some code that does that. Often when I talk about this, people who are familiar with doing these kinds of simulations will stop me and say, where's the step where you take the Cholesky decomposition of the matrix and use that to do your sampling? Basically, commons math is handling all of that for you and figuring out how to do the correlated sampling for you. There's like a goblin underneath this podium. So as you brought up, we can use fancier things. We could use a multivariate T distribution if we wanted to have fatter tails, and then we could use historical approaches to generate distributions that more closely fit the historical structure of the data. Once we have this, we basically have all the building blocks now. We have the process that we use to randomly sample market factor returns. We have the process that we use to take market factor returns and turn those into instrument returns. Now we just want to run this on Spark. So we'd like to be able to run a ton of simulations in parallel, millions, billions, possibly trillions. The best way to do this in Spark is probably to create an RDD of seeds. So create a distributed collection of, let's say, if the size of your cluster, you have 10,000 cores, then you create 10,000 seeds. Use each seed to generate a set of simulations. So you take each seed, you throw it into some random number generator like a Mersenne twister. Commons Math has a really nice implementation. And then you use each seed to generate a set of simulations. Finally, having run the simulations and figure out the return for each particular simulation, you can run aggregations to get the results, either in total or filter down to subsets of your portfolio, different set of criteria. So this is a function that shows us how to get the return for one particular trial. So we generate a state of the world, a trial, a scenario. We have this factor distribution, which is sampling from the multivariate normal distribution. We go over all of the models. So we want to understand for our whole portfolio, for every particular instrument, we plug in the particular linear model that we trained for that instrument, sum over the entire results, and the number that we spit out, this total return at the bottom, is the sum of all the returns for all our instruments for that particular simulated scenario. Any questions on that? Cool. So you said, how can we do a what? An evolutionary kind of, I guess I haven't thought about that. So you'd say for 10 seeds, generate some particular result, and then how would you use that to generate the next results? So yeah, I'd have to think about that a little bit more. I'm not familiar with approaches that do that. I think basically you want all your simulations to be independent, so you wouldn't necessarily want to use the results of previous runs to affect future runs, because your model basically assumes that each simulation is totally independent from all other simulations. But yeah, we can talk about that more. Maybe I'm not thinking about some aspect of it. So with that basic function that's able to generate our trial returns, we'd like to basically run that in parallel across the cluster. We start by using this Spark feature called broadcast variables, which basically allows us to take some object that is on our driver process and broadcast that to all the executors in our program. So once this broadcast process is complete, we have that variable in local memory on each executor, and we don't need to transfer it each time that we want to run a task. We generate our RDD of seeds using parallelize, and then we create a RDD of trials by basically applying this trial returns function to every set of seeds multiple times. Let's look a little bit at how this gets executed on the cluster. So for those not familiar with how Spark works, Spark basically has a set of executors that are distributed across the cluster. Each executor is a JVM and has a set of slots, a set of cores that it can run tasks inside. For each executor, we'll have a single instance of these model parameters like we talked about. Each executor will run a bunch of tasks both in sequence and in parallel, and each task will run a bunch of simulations. And then we finally use Spark to aggregate over the results of these tasks and these simulations. Any questions about that? Yeah, so the question was, does the running time depend on the longest running simulation? That is true. An advantage of, if you're able to split things up into small tasks, you can, if a particular task is running a long time, it doesn't necessarily stop the whole computation, because you can have other sets of tasks running at the same time as it. So you don't have a particular long pole bottleneck in that way, but you can certainly enter a situation where if a task is taking forever, it slows down the entire job. In this particular case, we'd expect what we're doing for each simulation, for each task, is pretty similar, so we wouldn't expect a ton of skew in how long it takes to process each task. So the question was, can we do partial result aggregations? Do you mean by that aggregating in the middle before we've completed? I don't think Spark currently doesn't have the ability to do that. There are accumulators. So I think once tasks complete, they can report the results. And if you have a bunch of tasks, you might be able to get some results before the entire set of tasks complete. But within a task, you certainly can't get any partial results without doing some fancy thing yourself. So because we'd probably like to analyze these trial returns, run a few different things over them, try to understand them in a few different ways, it's useful to use Spark's caching functionality, which will basically pin them into memory around the cluster. To compute the value at risk, we basically are sorting all of them and chopping off the bottom 5%. If we want to compute the expected shortfall, we're basically sorting all of them, taking the bottom 5%, and then computing an average over those, instead of just taking the max of that bottom 5%. This is a plot generated using the same techniques, the Scala breeze plot and kernel density estimation, to look at the overall distribution given our model of 2-week returns. And the var is basically a cutoff somewhere in that range that cuts off the bottom 5% or whatever extremity that we're interested in. So there's a lot of software that does this already. This certainly was not invented for use on the Hadoop ecosystem. Why would you use Spark in this kind of situation? What makes Spark and the whole Hadoop ecosystem an ideal tool for running this kind of computation, doing these sorts of calculations? One of the main powerful things is ease of use. So I like to explain Spark as parallel computing for 5-year-olds. You basically are able to write programs that leverage huge amounts of machines without thinking about the fact that you're doing that at all. You don't need to think about how messages get passed around. You just write some sort of function and say, distribute that over a cluster of thousands or tens of thousands of cores. Which is really, you can accomplish it in some ways in the HPC world, but there are no frameworks that are really as general and as fundamentally capable at handling large volumes of data anywhere else. The other nice thing is that it has a Scala and Python REPLs. So instead of compiling your code, a bunch of C++ code, running it on the cluster, seeing what results you get in like 6 hours, Spark makes it really easy to program against a shell. Basically, say I want to understand what this is doing right now and get answers pretty immediately. The other big draw of it is that you had a question. So I certainly, would not recommend having a production VAR simulation that's using Python. Often what you would want to do in that kind of situation, if you're really interested in using Python for the plumbing, is to optimize the core parts in C++ or use Python or something like that. And then just use Python for all the code around that. But I would expect it to be significantly slower, 5 times. I don't actually have a particular number. So the question is Spark using CPython or JPython? So Spark uses Py4j, which is basically a layer that allows a Python process to communicate with a JVM. That's all on the driver, so that's for the Spark's control plane. If you're going to use, if you want to run Python code that gets called basically in UDFs, that happens on the executors, and the executors will spawn little Python processes and pass the outputs between the JVM and the Python process through a pipe. In that case, it probably would. If what you're doing is fairly CPU intensive. If what you're doing is fairly data intensive, then the extra cost of serializing it and sending it over the pipe can be an additional overhead. Any other questions on that? The other draw, and maybe the bigger draw of Spark, is that it allows you to do sort of all the different functions that are required for both doing these calculations, wrangling the data for them, and then looking at the results in a single platform. So you can take your large, huge amounts of data that come in that's very unclean, filter out what you care about, clean those results, impute missing values using Spark in a highly parallel way. You can fit the models as we demonstrated. You can run the simulations as we demonstrated. And then also extremely importantly, you can analyze the results. So instead of, in our particular situation where we sucked a single number into the driver, a more common model of processing for this is to actually write out the results of all the simulations to HDFS. Then you just have them there. You can pin them into memory if you want using HDFS caching. And then you can later come along and run Spark jobs over that data and aggregate along particular dimensions that you care about. Let's say, look at all the instruments in California. What is the VAR for them? Look at all the instruments that are options that have to do with currency. And that's probably the more common use case in production deployments of this. So this is something we talked about before. A worry that often comes up is, but it's CPU bound and we're using Java, or even worse, we're using Python. The most computationally complex operations are normally in matrix operations. Those can be delegated down using JBlast, using some sort of framework like Breeze or NumPy. You can call it the GPUs just like in C++. And if you really want to, you can JNI out to C++ itself. And then the other common worry about the JVM is that garbage collection can really slow things down and be difficult. The particular patterns that are often used to run these simulations are not particularly memory or garbage collecting inducing. We're not generating tons of objects, storing them in complex data structures. We're generally processing data, doing our calculations in a streaming fashion. So you want to be like Teddy Roosevelt, independent, and do this yourself. How would you get started? One thing that I should update this link actually. I've been working on a Spark Finance, Spark time series project that basically makes it really easy to take Spark and do all sorts of basic time series transformations and perform these kinds of calculations. It's in its infancy, but there's a lot of exciting stuff to do there. And then to toot my own horn a little bit, we recently wrote this book, Advanced Analytics with Spark. There's a whole chapter in there that goes through a longer and slightly more sophisticated implementation of this use case, including a little bit of more statistical rigor, testing results, things like that. So I think, I think that's all I have. Thank you, everyone, for coming. Any questions? So the question was, when we're actually doing this data in our examples, we're using public or private data sets. So if we're implementing this in an actual bank, private data sets, but the examples in the book, the examples in the repo are public data sets, mostly just stocks downloaded from Yahoo.